Okay, so branch and bound is another algorithm designing technique. Generally, probably the last option before back brute force search. Okay, so what happens is, as you can see, the designing techniques that you have learned. So most of the time, greedy is kind of the best. Best if it is able to give you the proper answer, right? It takes less time. So greedy is the most efficient, greedy and divide and conquer. Next comes the dynamic programming in the picture, then backtracking, then branch and bound, and finally the brute force. So we have learned the brute force, the easiest way to code, but the longest way to execute, right? Branch and bound is so let's start about branch and bound. uh, some problems can definitely be solved quickly using branch and bound. One of them is 15 puzzle problem that we'll going to learn today as well. So what is branch and bound? So branch and bound is similar to your backtracking technique. Okay, so as in backtracking, we generated some state space tree, right? But in branch and bound also, we also generated the state space tree. But the difference is in branch and bound. In backtracking, the state space tree was generated in a depth first manner, right? So once an expanding node generates a live node, that live node then and there becomes the next expanding node, and until that next child node finished exploring all its subtree, uh, the parent node did not become the expanding node again. Okay, so this is kind of breadth first way, depth first way, but here actually we'll have the uh, BFS way. Okay, so we'll see how it will go on in branch and bound, how the state space tree is being searched in branch and bound. Okay, so in state space, in branch and bound, all the children of an e node or expanding node are generated before uh, any other live node become e node. Okay, so for a node, all the possible children are generated first, and then only we move. So until all the children are generated, it remains the e node. So once all the children of it are generated, then some any of the children becomes the next e node for expansion. Okay, so there are two steps involved in branch and bound. One is your branching. So branching is the way of generating the next state to find the feasible solution. Okay, so from an e node we generate all the possible options for that expand e node. Okay, and that generating the possible options, or generating the possible states from the current e node is known as branching. Okay, and next is bounding. Bounding is actually finding the upper bound and lower bound of the feasible subsolution. So once we generate a child node, and we try to find out what is the upper bound or lower bound for this node. Okay, and from that information we can also we can also use this information, that what will be the upper bound for this solution and lower bound for this solution. Based on that information, we can discard some of the node for further expansion. Okay, so this upper bound and lower bound information actually helps us to bound the nodes. Okay, uh, another term that we'll get to know is about pruning. Pruning is nothing but discarding the node which does not have the probability or possibility of getting a good answer. Okay, how it is determined? So suppose if a lower bound of a problem state is greater than the upper bound of another problem state. Okay, so suppose for this node there are some we have derived its lower bound and upper bound. Okay, that how many steps is at least required from this step to generate the answer state, and upper bound is how many maximum number of steps required from this node to find out the answer node. Okay, similarly, suppose we have for another node we also found some lower bound and upper bound. Okay, that this node 2 also has some lower bound and upper bound of generating the solution. Now if we found that if a lower bound of a problem state is greater than the upper bound of another problem state, suppose this lower bound of this state is greater than the upper bound of this state, okay, so obviously this will be taking much larger time than this one, okay. So what we'll do, we'll discard this node for further from further expanding, okay. So this is what is called pruning. So if we found that lower bound of some state is greater than the upper bound of some other state, then we can stop expanding that first node, okay. So that is what is called pruning. So this branch and bound technique is mainly and generally used for solving optimization problem and mainly for minimization problem. Uh, so you will see if you take operation research as your option, you do not have probably in your next semester. Operation research probably you have in 7th or 8th semester, okay, and that is also an available an option, and I teach that subject as well. So if you take operation research as your option, you will see that there are optimization problems. You also already have seen optimization problem in terms of your knapsack problem, right? That is one example of optimization problem. Job sequencing is another optimization problem. So optimization problem is that kind of problem where there is an objective function which we try to minimize or maximize, and there are some constant, okay. So this kind of optimization problem can be solved using branch and bound. And generally minimization optimization problems are of two types. Sometimes the objective function is required to be maximized, and for some other problems the objective function is required to be minimized, okay. So generally minimization problem can be efficiently solved using branch and bound technique. But again any maximization problem can be converted to minimization problem by negating the objective function and the constant as well. So that is not a deal. You can solve both of them by converting maximization to a minimization problem and solving them, okay. So uh, so you will see that traveling salesman problem and this kind of problem, which are generally minimization problem, can be solved using branch and bound, okay. So there are three ways we can implement an branch and bound algorithm, and that three ways generally depends on how we are branching, okay. And the three ways are FIFO branch and bound, and that will use queue, LIFO branch and bound, that will use stack, and the least cost branch and bound, that will use priority queue, okay. So probably we do not have any session on priority queue, so we'll give a brief idea about priority queue prior to doing the least cost branch and bound. But anyways, so these ways, FIFO branch and bound, LIFO branch and bound, and listwise branch and bound, are basically ways we are doing branching, ways we are expanding the node, okay. So the categorization is dependent on that way of branching, okay. So let us first see about FIFO branch and bound. So FIFO means first in first out, right? So the state space tree is searched searched in FIFO manner. Okay, so we'll get a node and we'll generate all its children, and then whichever children is generated first will become the next e node. Okay, so that is the concept. So how will you do that? So for doing that, we need an queue to hold the state that has been generated, and this will be exactly same as the BFS search manner, okay. So the FIFO branch and bound is exactly same as BFS manner, but rest of the branch and bound techniques are not exactly as BFS manner. We'll see, okay. So how we'll do that? So we'll start with the root node, that is the initial state, and an empty queue, and then what we'll do, we'll push this we'll enqueue this empty queue with this root node, okay. We'll enqueue the root node in this queue, okay. So we'll have a root node, suppose root node is 1, and we'll have a queue to start with, and we'll push will not push, we'll actually enqueue this queue with this root node, and then we'll iterate through this queue until the queue is empty. What we will do, so now you have at least one element which is the root node, so we'll dequeue to get the e node. So from that we'll get the e node, Okay. So we'll dequeue the queue to get the e node, and then we'll start expanding that e node. Okay. So generate all the children actually, all the children of the e node one by one and check. So now for this e node, for this node, we'll generate all the children possible. Okay, we'll generate all the children possible, and we'll check that if the child is not killed by bounding function, then we'll enqueue with this node. Okay. So we'll generate one of the children, and we'll employ the bounding function to check whether this node can lead us to a valid answer node or not. So if the bounding function bounds it, that no, it cannot give us a valid answer, so we'll not enqueue it in the queue. Okay, we'll generate the second node and check whether it is bounded by the bounding function. So if it is not bounded by the bounding function, then only it is, if it is not killed by the bounding function, then only we'll put it into the queue. So that will be done for all the children that has been generated. Okay, so we'll generate all the children of the e node one by one and check if the children is not killed by bounding function, we'll enqueue this node. Okay. So the way the children are generated will be put into the queue one by one if that is a valid node, and in the loop again. So once this is done for current t node, so in the loop what it will do, it will take the next t node from the queue, right? So the next children, the children that was first enqueued in this queue will be taken as the next expanding node. Okay. So we'll see an example. So suppose this is a board. So what we'll do, we'll see the example of 3 queen problem. Okay. So we did last day in backtracking 4 and 8 queens problem, or in general n queens problem. So we'll see this example with a 3 queens problem. However, 3 queens problem is there is no possible solution for 3 queens problem, but we'll see this example to get an idea of how the states are generated in FIFO branch and bound. We'll also use this 3 queen problem for to get the idea of LIFO branch and bound. Okay. So this is a 3 queen problem, and we'll see how branch and bound, FIFO branch and bound will work with this problem. So this is the initial state, there is no queen is there. So this is the root state. So what we'll do, so we'll have a queue with us. Okay. So this is our queue. So we'll have queue with us, this is our queue, and whenever uh, so at first what we did, we enqueued the queue with the root node, right? So that we have done. So this is our current state. Now what we will do, we'll dequeue this queue, right? So we'll dequeue this queue and get the e node. So our current e node is 1. So next what we'll do, we'll expand this e node. Okay. So I have used 3 color code for the node. Green is the live node. Okay. Yellow is the expanding node or e node, and red is the dead node. Okay. So let's see. So now 1 becomes the expanding node. So what it will do, it will generate its state one by one. So it generates, so it places the first queen at the first row and first column. So this is our second state, and we'll check that by the bound. So once it is generated, we'll check by the bounding function that whether it is a valid configuration or not. So now so for this configuration, it is valid configuration till now. So we'll push it into the queue. Okay. So we'll push it into the queue. Okay. So now we'll generate the next children of next child of 1. So it will put in the second column, right? The queen in the second column, and then we'll check whether it is a valid configuration till now. Yes, it is a valid configuration. So we'll now put it into the queue. Okay. And next we'll generate the next possible state. So this is your fourth state. Okay. So this is also a valid configuration. So we'll put it into queue. Okay. Okay. Now there are no more children that we can generate from this node 1, right? So node 1 now becomes an dead node. Okay. So what will happen now? So now it will check whether the queue is empty. So queue is not empty, right? So it will dequeue the queue. So this was our front element, right? So 2 was our front element. So it will take 2 as an expanding node. Okay. So 2 is now extracted from this queue, and it is now serve us as an expanding node. So now 2 becomes the expanding node, and it will generate its children one by one. So it will first place in the first column. Okay, second row first column. So is it a valid configuration? No, right? Because both the queens are in the same column. So we cannot, the bounding function will bound this state. Okay, so the 5 will not be inserted into the queue. Next, it will generate the its next children. So what we found that these two queens are in the same diagonal. So this can also be not a valid configuration. Okay, so the bounding function will kill this node as well. Next, we will generate this state where the second row queen is placed on the last column. Okay, third column. So this is a valid configuration, right? Because both of the queens are not discarding each other. So we'll push this state into the queue. Okay, so we are pushing actually the whole state, not the number. So if we implement it, we have to implement it like that way. Okay, so we have to keep track of the all the things. Okay, so numbers are just the representational thing over here. Okay, so anyways, so now all the three possible options for node 2 has been generated, right? So node 2 will now become a dead node. Okay, so it has fully been explored. So so what will happen, it will now check whether the queue has become empty. Queue have not become empty, so next element that will be extracted from queue is 3, right? So now 3 becomes our next node, expanding node, and we'll expand the possible children of this 3. Okay, node 3. So now it will put the second row first column. So what we can see that this is not a valid option, right? So 8 will be killed by the bounding function, right, and will not be pushed in the queue. Next we'll generate the second option, second children of child 3, which is this one. So we can see that both the queen in the same column, so bounding function will kill node 9. Okay, next it will generate the third column. So here also you can see that they are in the same diagonal, so bounding function will kill this again, right? So none of the children that has been generated by expanding node 3 can be pushed into the queue. Okay, so what will happen now, all the children of the node 3 has been generated and it will become the dead node. Okay, so now it will check again whether the queue is empty. So queue is not empty, so 4 will be taken out of queue and will be treated as the next expanding node, right? So now the fourth node will be treated as the next expanding node, so it will generate its first children. So now it is now expanding node, so it will generate its first children. So what we can see that this is a valid configuration, right? These two are not cancelling each other. So since this is a valid configuration, it will be put into the queue. Okay, so it is now put into the queue. Next it will generate its next children, but this is not a valid configuration. They are cancelling each other, so it will be cancelled out by the bounding function. And then the final one for this node 4 will be generated, which is also not a valid option, right? So it will be discarded by the bounding function. Okay, so now we have done generated all the children of node 4. So we'll the node 4 will be a dead node now. So once a node become dead node, an expanding node become dead node, we check the queue. So queue is not empty yet, so the next node that will be expanding node is 7, right? So 7 is now become the expanding node. Okay, so we'll generate the children of the 7 one by one. So let's see. So first we'll put in the first column, third row first column. So here we can see that this both two are in the same column. So this is not a valid configuration. So 14 node will be a dead node. Okay, next we'll generate it by the second column, but here also these two are diagonal, so this cannot be a valid option, so will be bounded by the bounding function. Okay, will be killed by the bounding function. And next we generate the third option. So here we can see that this is also not a valid configuration, because these two queen cancelled each other, so 16 become an dead node as soon as it is generated. Okay, now all the children of node 7 has been generated, so it will be now a dead node. Okay, so next once a dead node once a expanding node becomes dead node, we'll see the queue is empty or not. So queue is still not empty, so we'll take the element out of the queue, and our next expanding node is the node 11. Okay, so we'll generate node 11 one by one. So this is the first child of the node 1. So you can see that this is not a valid configuration. Okay, so both of them will cancelled out. so it will not be pushed into the queue as well. So next, the node 18 is being generated. So here also we can see that both of them are in the same diagonal, so this is not a valid option. It will not be pushed into the queue. And finally, the final option for this node 11, final child of the node 11. So this is also not valid configuration, right? Because both of the queue in the same column. Okay, so both of the queen in the same column. So what we will have? So we can bounding function will again bound the node 19. Okay, so all the child of the node 11 has been generated. All the children of the node 11 has been generated. So we'll see. Uh, so node 11 will become the dead node. Okay. So now we'll come to the queue, and we found that there is no option. I mean, no element available in the queue, right? So there is no expanding node available for now. So we've completed our state space search, and we found that there is no valid solution for a 3 queen problem. Okay, but the objective of mine to show this example is to give an idea how the state space are generated using FIFO branch and bound, and and how the search occurs. Okay, so this is such kind of this is exactly how the BFS search occurs, right? If you have previously done the BFS search in your data structure course, you might know. So this is how the BFS search work, exactly same. Okay, now what we will do, so next thing we will do is the LIFO branch and bound. Okay, so LIFO branch and bound will employ queue in place of employ stack in place of queue. Okay, so the state space search will be done in a LIFO manner, but uh, so for doing that it will employ a stack, and the search will call D search. Okay, now don't get confused, but this is not DFS search. Okay, in DFS search what happens? In DFS search, from a node we generate a child, and as soon as we generate the child, we make this an expanding node, and we generate its child again, right? So as soon as we generate this, so it becomes the expanding node, and so on. It will generating like that. So once this all the children of this has been generated, next we come back here and see if any other child of it has alive. Okay, so if there is any other child, so they will be in the will be searched next. Okay, so this is how the DFS search will work, right? But we'll see that in this search in LIFO branch and bound, it will not go like searching a branch as long as it can go. Rather it will be a mix of DFS and BFS. Okay, so what it will do, it will generate all the childrens of a node, and it will get into one depth and find out all the childrens of that possible node. So let us see. Okay, so let us see how we'll see an example for that with the same 3 queen problems. But prior to that, let us see how LIFO branch and bound is done using stack. So the same approach, we will start with a root node or initial state and an empty stack. Okay, and we'll push that root node into the stack. Okay, and while the stack is not empty, we'll pop the stack to get the expanding node, and we'll generate all the child of that expanding node. So there is the difference. The difference between this search and DFS is that we generate all the child of this expanding node. Okay, in DFS we generate one child, and then and there we try to expand that child. Okay, but here we'll generate all the child of the expanding node, and then we'll check one by one. One by one, what we'll check? We'll check that whether it is killed by the bounding function or not. So if it is not killed, we'll push it into the stack. Okay, so you can see that the structure for FIFO, LIFO, and list cost search, list cost branch and bound will have the same structure of algorithm, but the way of implementation is different based on the data structure used. In FIFO we used queue. In LIFO will use the stack, and we'll see that how the search has been modified for using the stack. Okay, so let us see with the same example. So here we will have the initial state where no queen is been placed. Okay, And now what we will do, so we'll put this initial state into the stack. So this is the stack. Okay, so this is the bottom of the stack, and the stack will fill up in this way. Okay, so what will happen, so we'll pop the next node from the stack. So that is node 1, and we'll start expanding all its children. Okay, so we'll start expanding all its children. So now node 1 will be expanded. So now so it will generate this node 2. So this is a valid node, right? So if it will not be bounded, it will not be killed by the bounding function. So it will be pushed into the stack. Okay, so now node 2 is pushed into the stack. Okay, so now node 1 will generate its next children. So this is also a valid configuration. So this will so node 3 will be also pushed into the queue. Okay, next it will generate its next children. So this is also a valid configuration. So node 4 will pushed into the stack. Okay, so now all the children of node 1 has been generated. So node 1 will become dead node now. Okay, so next what will happen, next we'll pop out from the queue, right? So from the stack, right? So the stack, in stack, whenever we are popping out, we are popping out the last element that is inserted, right? So the last element that we inserted is 4, right? So the next node will become the 4. Okay, so this one becomes the next node. Okay, so we'll now start expanding this node. Okay, so you can see the difference. In FIFO we start next we start expanding node 2, but here we'll start expanding node 4. Okay, so we'll generate all the children of node 4 one by one. So let us see. So now this is the expanding node. So the first children that we are generating is this one. So this is a valid configuration, right? So we'll push this node 5 into stack. Okay, so we have pushed it. So next what we'll do, we'll generate its next children. So this is not a valid children, right? Valid child, right? So it will be killed by the bounding function. Next we'll generate its next children. So this is also not a valid configuration, because both of the queen in the same column. So node 7 will be killed by the bounding function. Okay, so now we have generated all the children of node 4. So node 4 will now become the dead node, right? So as soon as a expanding node become dead node, we come to the stack and we'll check whether it is empty. So this is not empty. So we'll pop out the last element, right? So that is 5. So next expanding node becomes 5. Okay, so this 5 becomes the next expanding node. So you can see this is a mixture of BFS and DFS, right? It is doing whenever a node is expanding, that is expanding in a BFS manner, but the next node that will be expanded is searched in kind of DFS manner, right? So now what will happen, it will generate its children one by one. So now 5 becomes the expanding node, and the first children is generate is not a valid one, because both of the queens at the same column. So bounding function will kill node 8. Next it will generate this configuration, which is again not a valid option. Both these two queens are in diagonal. So bounding function will kill node 9. It will not be pushed into stack. Next it will generate the final children of this node. So this is also not a valid configuration. So bounding function will kill node 10. Okay, so all the children of node 5 have been generated. So now node 5 will become a dead node. Okay, so what it will do now, it will now come back into the stack and it will check what is the next node to be expanded. Okay, so it will pop out the option. So the next node will be node 3, right? So now node 3 will be expanded one by one. So now the first children, when it is generated, so this is not a valid configuration. So it will not be pushed into the queue. Okay, it will be a dead node and killed by the bounding function. So we'll generate the second node of this. So this is also not a valid configuration. So bounding function will kill that and will not be pushed in the stack. Okay, and this is the third child. The same again, this is not a valid configuration, will be killed by the bounding function and not pushed into the stack. So now node 3 has expanded all its children. So it will now be killed automatically. So once it is killed, we will come back to the stack and we check whether it is empty. So this is not empty, so it will be popped out, right? So node 2 will be popped out, and next we'll expand node 2, right? So first child will generate from node 2 is node 14, which is again not a valid configuration, so will be killed by the bounding function. Next node that will be generated is this one. This is also not a valid configuration, so it will be killed by the bounding function. And the final node of node 2, which is node 16, you can see this is a valid configuration, right? So node 16 will be now pushed into the stack. Okay, so once node 16 is generated, node 2 is completed, right? All its children has been generated, so node 2 will be a dead node now. So as soon as it become dead node, it will come to the stack. It will see whether the stack is empty. So since the stack is not empty, it will pop out. So it will pop the node 16 out of it. Okay, so now node 16 will be the expanding node and or e node, and it will try to expand this. So we will have so we'll generate node 17 from node 16. So we can see that this node 17 is not a valid node. Okay, so since both of the queen in the same column, so we'll bounding function will discard this or kill this node. Okay, so the next queen next configuration that will be generated by node 16 is 18, which is again killed by the bounding function, right? So it will not be pushed into the stack. So final node that has been generated by the node 16 is this one. So they are in the same column, right? So this is not a valid node, hence it will be killed by the bounding function. So once all the node of node 16 is generated, so node 16 will be a dead node now, and this is how we search. This is how the LIFO branch and bound works. Okay, so you can see the difference. You can see the difference by the number by the number in order in which it is generated, right? So 1 2 3 4 is same as FIFO branch and bound and LIFO branch and bound, but in FIFO branch and bound node 5 was this one, right? Which is node 14 in LIFO. So here the node 5 is this one. So the way it is searched, the way the states are generated has changed using stack. Okay, so that is the difference between LIFO branch and bound and FIFO branch and bound. We use stack, and we use in LIFO we use stack, and in FIFO we use queue, right? So that's why in the FIFO it gives similar result in BFS, but in LIFO branch and bound we found a mix of BFS and DFS paradigm, right? Okay, so now we'll get into the our third technique, that is your least cost branch and bound. So prior to going into the least cost branch and bound, we have to know what is cost, right? So we'll now introduce ourselves to the cost function. So what we see for the previous two example, previous to LIFO and FIFO branch and bound, we see that the selection of next e node in both for both the FIFO and LIFO branch and bound is blind, right? It is blindly generating the states, whichever it is found in the queue or in the stack as the next node, it is generating from that node, right? So it is not giving any preference to a node which has a good chance of finding an answer. So that is what this FIFO and LIFO branch and bound do. It is not taking any. It is not taking the configuration of the current status into consideration, right? So the configuration is not taken into the consideration. It is that's why it is generating the next node is randomly. Okay, so what we'll have to do, so here now we'll introduce some cost function. Okay, so let's see. So what we'll do, we'll introduce an intelligent ranking or cost function CCAP. Okay, that can be used to determine the next node. Okay, so CCAP will use to determine which node will be the next node. So CCAP will rank each live node, and next node will be selected based on the value of the best value of the CCAP for all the nodes. Okay, so we'll be generating a node from an expanding node, and we'll try to find out what is the CCAP value of that node. Okay, and that's how we'll have the CCAP value or the cost value actually for all the nodes currently live. So from that live node, whichever node has the best CCAP value or best cost value, we select that node for the next e node. Okay, that's the idea or that's the concept. So how to define the CCAP function? So that's come the problem. So what will be an idea to define the CCAP function, the cost function? So obviously the cost function should be such that it should represent the computational effort that is required to reach an answer node from a node X. So if CCAP X is the function that denotes the cost from for node X, okay, so it should be very logical that CCAP X gives us the computational effort required to reach an answer node from the node X. Okay. Uh, okay. So what we will have? So this involves searching the state space subtree rooted at node X. So what we are telling? So we are telling that we are trying to find out what is the cost of this node. Okay. So the as we told, the cost of this node is to is the computational effort that is required to reach an answer node from this node, right? So to reach an answer node, what we have to do, we have to expand all these children, right? So we have to expand all the subtree rooted at this node, right? So this subtree has to be expanded, and this subtree has to be find out what will be the computational effort to required from this node to some answer node. Okay, what I'm trying to tell, suppose this is the expanding node currently, and this is the answer node. Okay, now when you generated this node from its parent, and then what we are trying to do, we are trying to do find out the what is the cost of this node, right? Now the cost of this node is defined as the computational effort that is required from this node to reach the answer node. Suppose this is an answer node. Okay, so what is the computational effort for so the path that it has can should be the computational effort, right? But how, when you generate this node, how do we know that how after how long the answer node is there? There is no way we can know that, right? So to know how, at which distance this answer node belongs, we have to explore all this subtree of this node, right? So we have to expand the node, and we have to find out where the answer node belongs, right? So so this actually involves searching the whole state space subtree rooted as X, right? So the subtree rooted at X has to be find out to find if there is an answer node and how long there it is. Okay, so therefore CCAP is no use, right? Because the cost function, if you try to find out how far it is not is actually requiring the subtree to be generated itself, right? So we are trying to find out whether we should expand it or not, and to determine that we have to expand this node, right? So that's why the such CCAP is no use. Okay, so the cost value is no use. So what we'll do, so in place of being exact, we'll redefine CCAP to have an estimated value. Okay, so we'll not tell for guarantee that this answer node from node X is is 3 node away from this node or 4 node away from this node with an guarantee, right? We'll tell that this is an estimated value from this is an estimated value to reach the answer node from this current node X. Okay, so in place of being exact, we'll redefine the CCAP to be an estimated cost. Okay, to give an estimated cost. So next thing is we'll look into it. So how we'll make an estimate of it. Okay, so what we'll do, so we'll redefine the cost CCAP X as two function. Okay, one is hx, another is gcap x. So what are hx and what is hx and what is gcap x? Okay, so hx is the cost of reaching the node x from root. Okay, so what we are doing, we are exploring the state space tree, right? So from root we are expanding the node one by one, and suppose this is our node x. Okay, suppose this is our node x. So hx function will give the cost of reaching node x from the root node. Okay, so if we take the cost as the path, uh, so what will happen? So from root node it takes two edges, right, to reach to node x, right? So hx for this example will be 2. Okay, so hx denotes the cost of reaching node x from root. So this is an exact value, there is no estimate for hx. Okay, this is an exact value. Now the thing is g cap x. So g cap x gives us the estimated cost of reaching an answer node from node x. So from node x, how far the estimated how far an answer node can be, gives us the estimated answer node. Okay, so suppose this is the path. So here the estimated answer node, the cost of estimated answer node will be 4 for this example. But again, gcap gives us an estimated cost. Okay, it is not gives us the exact cost. We do not know whether it is exactly after 4 nodes or not. Okay, so what we will see, so we'll now see how this estimation will be done. So this estimation will be done based on problem to problem. uh, our next example for list cost search is basically 15 puzzle problem. So we'll see that how this estimation is done for that case. Okay. Okay, so next is so state. So what we'll do? So we'll generate this cost value for each the node, and a state with least lower cost value is expected uh, to nearer to the node, right? So because the cost value estimated the how much cost it will record. So the lower the cost value is, it is expected that it will be closer to the root node. Okay. So what we will do now? So the live node with the lowest possible cost value will should be chosen as the next e node. So we'll generate the next e node that will be selected will be based on the lowest possible c cap value. Okay. So if there is a tie, we can break the tie arbitrarily. So if there are two, three, or more than one node actually, if there are more than one state which are having same cost value, which is the lowest one, we can make the tie arbitrarily. You can choose any one of them. So since we are taking the lowest possible cost, that's why it is called least cost branch and bound method. Okay. And we can also consider this LIFO and FIFO and LIFO can be a special case of least cost branch and bound. So how? So when g cap x is 0 and hx is the level of node x in state space tree, then least cost behaves as FIFO. So what it is telling? So it is telling, suppose this is a node. Okay, this is the root node. It has generated two children. Okay, so for these two children, since they are in the same level 1, so hx will be 1, right, for these two children. Now what it is telling, if gx is 0, so we do not have gx for any of the nodes. Okay, so we have generated two children from this root node, and we have hx gx is equals to 0 and hx equals to 1 for both of them, right? So there is now tie, so we can select any one of them to expand further. Okay, so generally we select the first one, that is expanded further. So it will now expanded further, like so for this two node that has been generated, we will have hx value as 2, right, because it is the second at a distance from distance of 2 from the root node, right? But again, this node will not have any gx value, right? So the cost will be 2 itself. So these two have 2 and the least cost is 1, right? This is also a live node. So next this node will be expanded. So you can see that whenever you will have this g cap x as 0 and hx as the level of node, so this will gives you the same explode same it will explode the state space tree same as the FIFO branch and bound. Okay. And if hx is equals to 0, now if you do not consider the level, the distance from the root node of the current node x. Okay, and gx is g cap x is greater than y whenever y is a child of x. It means, see, y is a child of x. Suppose this is y and this is x. Okay, so g cap x gives me the estimate of how far the node is, right? So g cap x in this example g cap x will obviously one node higher than g cap y, right? So value of g cap x will always be greater than or equals to g cap y, right? Because y is the children, so whenever y is a child of x, g cap x will always be greater than g cap y, because g cap x is the parent, right? So it will take more time to reach from the x node to the child node, to the answer node, rather than y node to the answer node, right? So that's why it will behave as an behave in this case, it will behave as an LIFO. Okay, so what we will see, so if you do not consider the level value, if you only consider the child, I mean consider the estimated value, so what will happen, suppose for this node this child will be generated, right? Now this will have g value, the root will have g value which is higher than this currently uh, সৈকত is asking something, স্যার equal to টা কেন আসছে? Okay, so you will see that this will be greater than, either greater than or equals to, because not always actually I mean you, this is an estimated value, okay, you cannot guarantee it can be it cannot be actually what I can say is non decreasing or non increasing kind of value. It can be equal, but it cannot be greater than that, okay. uh, so this is an estimated value, so that's why so what will happen, see this g of this root will be greater than g of this greater than or equals to g of the its child, okay. So since for the next expansion what will happen, so this child will have less g value, right? So this will be least cost. So suppose this is 4, so this can be 4 or 3. So suppose this is 3, so it will now be expanded further, okay. So when it expand further, suppose this node is generated, so it will have the cost less than or equals to its parent, right? So suppose this will be 2, so like way it will behave like a depth first search, okay, or same as LIFO. So anyways that is just for your information, will not much of help for our study, okay. So anyways ccap x, or the cost function, is generally chosen such that it serves as a lower bound of the original cost. So generally the cost function, estimated cost function that we are deriving here, is basically the original is basically the gives us the lower bound than the original cost function, okay. So that means it will tell you that you list for a node you require at least this seek up x of movement to reach out the answer node, okay. So this will be the least value, so the original movement may be greater than seek up x, so seek up x will give you the lower bound of the original cost, okay. So next we'll see the example of 15% problem to get the idea of how least cost working, okay. So have you seen this 15 puzzle, this kind of 15 puzzle in our childhood days, in the fair of Rathar Mela or any Poush Mela, in this kind of melas you can find this 15 puzzle is being sold in various shops, okay. You can maybe still find in various shops nowadays, not an issue. So what is an 15 puzzle? So let me show an example which is available in the net. Okay, so this is what a 15 puzzle looks like. So a 15 puzzle have 15 tiles from numbered from 1 to 15 and a hole, okay, and an empty slot, okay. So what you can do, you can in that empty slot you can move it, you can move one tile, so you can move this one, you can move this one, okay. So you can move a tile adjacent to the hole into that hole, okay. So if you move that, so if you move 15 into this hole, so hole will be shifted this word, right? So that's how you can jumble up this puzzle, okay. So if you jumble it up, so it will give you an problem state. So what you have to do, you have to solve this problem, you have to take it back to the original configuration where the nodes are like this one. So nodes are from 1 to 15 in sequential order. Okay, so this is your solution state, this is your goal state. You have to find out the goal state from the problem state. Okay, so that is how you can shift the whole and find out and try to get the answer from it. Okay, so this is how a 15 puzzle problem is. You can do it. So the next thing is, how can we solve if we are given an initial state, initial problem state, and we have to get into this answer state. How can you get into that? Okay, so so let us give formally the problem description. So there will be it will consist of 15 number of tiles and an empty slot in a 4 cross 4 square frame. Okay, and we are given an initial arrangement of tiles. Okay, so initial arrangement means the problem state. Okay, it will be given to you. So this is suppose this is an initial arrangement of the tiles. Okay, so this is not in a proper arrangement, right? 1 2 3 4 5 6 7 is not there, 8 9 10 11 is not its place. So you can see that this is a jumbled up or in a problem state. Now we need to transform this into a goal state where each tile is placed sequentially from 1 to 15 and empty slot at 16 position. Okay, so this is what we have to do. So what will be a legal move? So a legal move is only a tile which is adjacent to empty slot can be moved to that empty slot. Okay, so as I shown you, so for this example, this is your empty slot, right? So you can move either 3 down to the empty slot, or 6 right to the empty slot, or 8 left to the empty slot, or 7 up to the empty slot, right? So there is 4 move available for this empty slot. Okay, but whenever empty slot is in a corner position or in a side, there will be 2 or 3 moves available to it. Okay, so so the legal moves is only a tile which is adjacent to the empty slot that can be moved to the empty slot. Okay, so this is similar to, we can tell that this is same as moving the empty slot towards left, right, or up or down, right? So in spite of telling that we are moving this one down or this one right, will be telling that we are moving the empty slot. Okay, so if you take 3 down to this empty slot, the empty slot will move up, right? So we'll represent the problem, or we'll think about the problem in there, in that we are moving the empty slot only. Okay, so now a state is reachable from its initial state if a sequence of legal moves from initial state leads to that state. Okay, so from this initial state, if the legal moves can lead you to the answer node or the goal state, then only it is solvable. Okay, so there is some formulas, there is some program to decide whether an initial configuration is solvable or not. Okay, so we will not focus on that. So whether the initial state is reachable I mean, sorry, whether the problem state is solution state is reachable from a problem state, we can also check, but we'll not focus in this lecture this one. Okay, so we'll assume that the initial configuration that are given to us is solvable. Okay, and then we'll try to solve it. And to solve it, we will employ the least cost branch and bound technique. Okay, so this is what it is. So to employ the least cost branch and bound for 15%, what we have to do, we have to find out the cost function, right? So as per LCBB means least cost branch and bound. Okay, so we found that the estimated cost function is divided into two parts. One is your the distance from the root node, another is your estimated distance of the answer node from X, right? So so what we will do, we will try to find out CCAP is the estimated minimum cost to search the goal node from the current state. Okay, so CCAP will give you the estimated minimum cost to search the goal node from the current state X or current node X. Okay, now CCAP will be will be summation of these two. So hx gives you the number of moves required to reach the current state from initial state. So this is what your hx will give you. It will give you the number of moves required to reach the current state x, okay, to from the initial state. So from the initial state, in how many moves you have reached to the current state is give you gives you the value of hx, okay. And more than that, we require how to define the estimated function, right? Estimated g cap x. So g cap x, will define g cap x is like the number of non-blank tiles that are not in that goal position. It means uh, we'll see an example. So it means that how many tiles are not in their goal position, how many tiles are misplaced from their goal position. That will give us the estimate of the number of moves that will be required to reach the answer node from the node x, right? Because see, the node x, suppose there are five suppose there are five tiles which are misplaced, right? So to reach from this node x where we have five tiles misplaced to the answer node, we have to move those five tiles at least once, right? Then we'll need at least five times to move the nodes, to move the holes, so that we can reach the goal state. So this is what this is why these non-blank tiles that are not in their goal position is chosen as your estimated cost function. Because in this example we need at least five. The number of moves may be greater than that. That will be dependent. But if five tiles are misplaced, or if n tiles are misplaced, we can say that at least n moves are required, right? It may be greater than that, but at least n will be required. So you can see that now this c cap x will giving you the lower bound, right? Not the upper bound. So this c cap x now giving you the lower bound, that how many move is at least required from this state to get into the answer state, okay. And for this 15 puzzle problem, we are taking the number of misplaced tiles which are non-blank, okay, is as our estimated cost value. So what we'll do, so with this cost function, we'll generate all the live nodes from the current expanding node, and we'll find out the cost of all of this generated node, okay. And then we'll advance with the least cost node that is generated and bound rest of the nodes, okay. So suppose this is an initial configuration given to you. So what we will have to do, we have to find out initially what is the cost of it. I mean, how much move at least required for this node to reach into its answer state, okay. So that will be given by our c cap x, right? So now see, c cap x is again divided into two part, h of x. So h of x is 0, right? Because this is the initial state. H of x gives us the number of moves required to reach the current state x from the initial state, right? So this is our initial state only. So h of x will be 0. Okay. Now what will be the g cap x? So g cap x gives us the number of misplaced tiles, right? So you can see that 1, 2, 3, 4, 5, 6, they are all in place. 7 is not there, right? So we'll not count it. So this is whole, so we'll not count whole. 8 is in its place, 9, 10 is in its place, 7 is not in its place, right? So one of them is not in its place. 11 should come over in place of 7, right? So 11 is also not in its place. 12 should be here. 13, 14, 15 is in its place. 12 is not in its place, right? So there are 3 tiles which are misplaced, right? So for this example, we'll have g cap x as 3, okay. So since 7, 11 and 12 are out of place, so that's why g cap x will give us for this initial state as 3. So for that initial state, we'll have now the cost of this node as 3, okay. uh, the summation of both the hx and g cap x. So now with this information, we will try to solve this initial state using the least cost branch and bound, okay. So how we'll do that? So this is our initial. So this is our initial state, right? Where we have cost is equals to 3. Okay, so the same table, same state that we have shown in the last slide. Okay, so now what we'll do, we can move this whole to upward, left, right, and down, right? So we'll explore them one by one. So let us first move to upward. So if you move this whole to upward, so 3 will come down, right? So 3 have come down and the whole has gone up, right? Okay, so this is the first option that we can do. The second option is downward. Okay, so we can move downward, so 7 will come up over here, right? So 7 will come up over here, rest of the thing will be there as it is. Next is suppose left, so 6 will come in the whole place and whole will be shifted towards left, and similarly right, so whole will be shifted towards right. Okay, so now once this four states is generated, what we'll do, we'll generate the cost function of it. So what will be the cost of it? So hx, which gives us the number of move required to reach this state from the initial state. See, hx is 1 for all of this, right? Because all this option, this one, this one, this one, and this one, required one move from the root node to coming to this node. Okay, so hx will be 1. Now we have to find out the g cap x for all of them. Okay, so g cap x is for this. If you look at it, so 3 is not in its place, 7 is not in its place, 11 is not in its place, and 12 is not in. So there is 4 tiles which is not in its place, right? So we'll have c cap as 1 for the hx, that is distance from root. Another is misplaced tiles. So misplaced tiles is 4, right? So summation of depth gives us the cost of this node, okay, which is 5, right? Okay, so in the for the second node, if you look at it, so again the hx will be 1, the g cap x will be so now we have 1 2 3 4 5 6 7 8 all of in its place. 19 is also in its place, 11 is not in its place, and 12 is not in its place. Rest of them are in its place. Okay, we will not consider the empty slot. Okay, so now there are 2 tiles which are not in its place, right? So the cost for this node will be 1 plus 2 is 3. So as soon as we generate it, we get to know that this is a better option than this one. Okay, than the first one. So we'll also generate the cost for the other two. So if you look at it, so again the gx hx will be 1 and g cap x will be, so let us see, 1 2 3 4 5, 6 is not in its place, so 1, this one 6, 7 is not in its place, 8 is its place, 9 10 in its place, 11 not in its place, and 12 not in its place, right? So 6 7 11 12, these four tiles are out of place, right? So the cost will be 1 plus 4 5, right? Okay, so for this node we have cost 4 5. Now the final one here, the empty slot is move to the right. So how many tiles are in its place? So up to 6 is fine, 8 is not in its place, 9 10 is place, 7 is not in its place, 11 is not in its place, and 12 is not in its place. Okay, so here also 4 items are not in its place. Okay, so we can find that the cost of this node as well 5, right? So what will happen, so we can found after generating the cost that this node has a better chance to come up with the solution quickly. Okay, so what we'll do, we'll next expand this node, okay, which is having the least cost. So let us again expand this node. So whenever we are doing the expansion, will not do the opposite of that of the movement that we have just done. So see, for this node we have come to this node by moving the empty slot downwards, right? So in its child we'll do not move the empty slot to upward, because this will lead us to the same node. Okay, this will lead us to the same node, right? So we'll try to avoid actually avoid the opposite move when we are trying to generate a child. Okay, because that will actually that will actually get into the loop. Okay, so if we allow the up move for this one, so it will next come up, and the in its child it will again go down, so it will keep on fluctuating up and down, up and down. Okay, so that's why we will not allow the opposite move in its children. Okay, Okay, so let us do the down move first. So if we move it down, so this is what we'll generate. Next we'll move left, we'll discard the up move. Okay, and next right. So there are three options available. Okay, so with these three options, what we can do, we can see that with these three options, we have to find out the cost. Okay, so we'll find out the cost. So all these nodes over here, all the states over here are two nodes away, two path away from the root node, right? So all the nodes are two path away from the root node. So h of x will be 2 for all of them, right? Now we have to find out the g cap x for all of them. Okay, so now g cap x for this node. So if you look at this state, so here we have up to 8 is fine, 19 is also fine, 15 is out of place, 11 is out of place, 13, 14 is 5, and 12 is out of place, right? So for this node, for this state, we will have uh, three tiles which are out of place, right? And the level of this and hx was 2. So okay, so I have this two. Anyway, so this has cost us 5. Okay, so if we generate for this node, what will happen? So again, the hx is 2, and these there are how many tiles which are misplaced? So up to 8, up to 9 is fine, 10 is misplaced, 11 is misplaced, 13, 14, 15 is fine, 12 is misplaced, right? This is fine. So there are three tiles, 10, 11, and 12, which are misplaced, and level is 2. So the total cost for this is 2 plus 3 is 5. Okay, and for this node which is already exposed, so you can see that there are only one node which is 12 out of place. Up to 11 it is fine, 13, 14, 15 is also 5, only 12 is out of place. Okay, so here the cost function will give us 2 plus 1 3. Okay, so what will happen now? So 2 plus 1 3, so the least cost having out of these 3 is this one, right? So this the least cost is associated with this node, so we'll expand this node further. What happened? Okay, there are some connection issue, I believe. Let me reconnect it.